Let's talk about eigenvalues and eigenvectors. When a matrix acts on a specific vector, something interesting happens. Sometimes the transformation simply stretches or compresses the vector without changing its direction. In this special case, the vector is called an eigenvector. The factor by which it's stretched or compressed is the eigenvalue. Think of it like this. Imagine a spinning top. The axis of rotation remains fixed even as the top spins around it. That axis is like an eigenvector. The speed of spinning is like the eigenvalue. It tells us how much effect the transformation has on the eigenvector. Mathematically, this relationship is expressed as x equals lambda x. To find the eigenvalues, we solve the characteristic equation, which is the determinant of a minus lambda I equals 0. Once we have the eigenvalues, we can find the eigenvectors by solving the equation a minus lambda I times x equals 0.
Alright team, our company's continuous stirred tank reactor requires optimization for a new reaction process. So what do you guys think? Can you guys do the stability and dynamic analysis for the CSTR reaction? Because our company needs it ASAP.
Alright boss, we'll do our best. We'll talk it.
I think we will be doing as soon as possible, okay?
Right.
So what do you guys think?
So what about we do some fluid dynamics analysis to save our reactor? Because I don't want to get in trouble. I'm just an intern, you know.
I think fluid dynamics will require a lot of computation on the code, which includes solving the Navier-Stokes equation. It will take a lot of time.
Thermodynamics? We tried that before for our previous sort of processes. Do you think thermodynamics will work?
Thermodynamics, yeah, it could work, but it requires the data from the process operation itself. Since we can't start the plant, therefore we cannot use thermodynamic approach.
How about we do plant process operation approach?
The time will do it. I don't think our boss is willing to risk another reactor for us to make another process plant, bro. Because the resources it would take, to create another process plant using another new reactor, it's a pretty risk considering we're not guaranteed the results. I don't think that's a good idea. Come on, we need to think of something else, something more productive.
So we have very few short times, and we have very short times and almost no experimental data. Okay, no experimental research. So what can we do?
How about eigenvalues and eigenvectors? That should be, I think we tried that before once. We experimented that, me and Mahmoud, we experimented that on a small basis, but I think it worked before. Didn't it, Mahmoud?
Yeah, I think this is a very good suggestion. Actually, since in most cases the process dynamics and stability depends only on concentration of the reactant and the temperature. That means we can use these as the eigenvector and get the eigenvalues for this. And if we get the eigenvalues, we can do the dynamics and stability analysis by solving the reaction kinetics equation.
I think you also save time as well, since we're already on the deadline itself.
So
Right, boss?
Yes, I agree with that.
Let's go.
Do you have anything to say?
Yes, I think that's a very good idea to solve our problem right now.
So let's prepare your drink, let's make mugs of coffee and start working. We need to do it as soon as possible.
ASAP guys, ASAP.
Continuous stirred reactor, or we call it as CSTR, is widely used in chemical process industry to conduct reaction where true mixing is required. The dynamic of a CSTR are governed by material and energy balance, which involve nonlinear couple differential equation. For the first order reaction, this equation depends on several parameters such as the reaction rate constant, inlet concentration, reactor temperature, and heat transfer characteristic. Okay, there are two objectives of the project. The first one is determining the steady state condition for the reactor, and the second one is applying eigenvalue and eigenvector analysis to the linear system to assess dynamic behavior and identify critical parameters influencing stability and response. Okay everyone, now Latini, you have to help me to use the material and energy balance equation. Okay, for Nalvin, you have to help me to do the calculation. And lastly, for Mahmudo, you have to help me to do the simulation. Okay.
I think that's all. We're good.
So he will do the material balance and energy balance.
Yes. Then I'll work on the eigenvalues and eigenvector to determine the both of the eigenvalues.
Okay, and finally I will do the I do this simulation to
run test the reactor process.
Okay. You well, everyone?
Yeah, we are all good.
Okay, next one.
Let's go.
Alright, so before we want to determine the steady state conditions for the reactor, there are two mathematical equations needed to do some analysis on it. So the first equation is the material balance, which is expressed as dCr over dt equals to Q over V in bracket Cr in minus Cr and then minus KCr, where Cr is concentration of reactant in the reactor, Cr in is the inlet concentration of reactant, K is the reaction rate constant, Q is volumetric flow rate, and then V is the reactor volume. So why do we do these equations? Because this equation allows us to determine the steady-state concentration of the reactant in the reactor. And then we have the second equation, which is the energy balance. It is expressed as these long equations where T is the reactor temperature, T in is inlet temperature, and delta H is heat of reaction. Rho is the density of the fluid, Cp is specific heat capacity, UR is the heat transfer coefficient, and finally Tco is the cooling temperature. And this energy balance equation helps us to determine the steady state temperature of the reactor. Since temperature influences the reaction rate, it directly affects the material balance, making the two balances coupled.
And now we are here to find the eigenvalues of the Jacobian matrix J, in which we have to solve the characteristic equation. The characteristic equation is given as determinant J minus lambda I is equivalent to 0, where J is the Jacobian matrix, lambda is the eigenvalue, and I is the identity matrix. Now, defining the Jacobian matrix J and formulating matrix J minus lambda I. So, matrix J is given as below here, as you can see. And to find J minus lambda I, we subtract lambda along the diagonal entries of J, which you can see here in the first and the fourth element, which is diagonal across each other, we subtract lambda. Next, we have to find the determinant of J minus lambda I. Since J minus lambda I is a 2 times 2 matrix, the determinant is calculated as AD minus BC, meaning we have to multiply the first and fourth term and subtract it with the second and third term. And so it will look something like this. Since the second term B is equivalent to 0, so BC will automatically turn to 0. So we end up simplifying, and here we have it. And so we have to set the determinant to 0 to solve for lambda. And so it will look like this, in which either the first term or the fourth term will be equivalent to 0. And now, solve for the eigenvalues of lambda. So the first factor is the first term of matrix J minus lambda I. So as you can see here, you have set the first element of it is equivalent to 0. And so you get your first eigenvalue as negative Q over V minus K. And as for the second factor, after solving this equation, you will get your second eigenvalue as negative Q over V minus UR P Cp over B. And so now, if you're going to determine the exact eigenvalues of lambda, using all the variable values given. And so, based on all these values, we can substitute Q with 30, V with 500, and K with 1. And so you'll get your first eigenvalue as negative 1.06. As for your second eigenvalue, after substituting all the values, that is 30, 500, 4, 700, 2000, and 500, you will get your second eigenvalue at very close to negative 0.06. And so, your final answers for the eigenvalues of the given Jacobian matrix J is negative 1.06 as well as negative 0.06. Both the eigenvalues are in negative form.
Hello, I am Mahmoud Hassan. As my colleagues already stated that we developed a mathematical model to analyze the dynamics and stability of continuous state time reactor based on eigenvalue and eigenmatrix approach. So to test our model, we have also developed a simulation code in MATLAB, so that based on the steady state reactor time parameters, we can check whether our model a process to a steady state process. That means either it is converges or diverges unboundedly. Therefore, if we execute the code, you can see that it allows us to enter some reactor parameters. Since it's a first order reaction, therefore the value of reaction rate constant is 1. Inlet concentration of the reactant is 20 mole per liter. Inlet temperature is 400 Kelvin. Volumetric flow rate 30 liter per second. Reactor volume 50 liter. And heat of reaction, since it's an exothermic reaction, therefore it's negative. Density 900 kg per meter cube, which is kind of mixture of higher hydrocarbons. And specific heat capacity 2000. And reaction rate, heat transfer coefficient is 4. And finally, the cooling temperature is 200 Kelvin. So under these conditions, under these reactor parameters, we observe that the model produces steady state concentration of the reactor as 1.1321 mole per liter and steady state temperature as 400.5241 Kelvin. And the eigenvalues of the system, the eigenvalue associated with the concentration of the reactant is negative 0.06, and eigenvalue associated with the eigenvector temperature negative 1.06. This negative value of the eigenvector is very important, since this negative value indicates that both concentration and temperature under small perturbation over a certain time, they do not increase unboundedly. Rather, they actually decrease and recess, and the system recesses towards a steady state process. Therefore, based on this simulation, we can conclude that our model allows the CSTR reactor to reach the stability and steady state process under a certain time. Suppose from the graph we can see that concentration of the reactor after certain times, approximately 3 seconds, it reaches to the steady state process, and in the temperature, approximately after 60 seconds, it reaches the steady state process. Therefore, given that the reaction condition remains unchanged, this reactor will operate without any stability issue. However, it is important to note that this model is only applicable for linear perturbation and small values of heat transfer coefficient. If the perturbation is non-linear or the reaction order is higher than 1 and the heat transfer coefficient is very large, approximately 50 or higher, then the model becomes unstable and the system especially the temperature, increases unboundedly, and which diverges the system and diverges from the stability. So, in conclusion, we can say that eigenvalue and eigenvector approach is very effective approach in analyzing the stability in a chemical engineering process in reactor analysis. However, and we like to thank the process manager to allow us to do this project, and thank him for his trust on us. This was a big project, and we tried our best to accomplish it as soon as possible. And we recommend that the reactor should go online on production as soon as possible to minimize the financial loss, and the reactor should operate under these certain conditions. If the reactor condition needs to be changed, then the process manager should again consult us for the calibration and optimization. However, we are looking forward to hearing from the process manager about the process update. Thank you all.